Okay, now we will get into the Pinacol rearrangements, and I already hear you asking, what the heck is a Pinacol rearrangement? It's a very specific kind of reaction that occurs in what we call 1,2 diols. Now, a 1,2 diol is basically any molecule where you have two separate alcohol groups on adjacent carbons. So this molecule down here, for example, is a 1,2 diol. We have carbon 1 with an alcohol and the adjacent carbon, carbon 2 with an alcohol. That's a 1,2 diol. Now, the kind of mechanism for this is that one of the alcohols is protonated first, and either alcohol can be protonated. For molecules that are symmetrical, it doesn't really matter which one. You'll get the same product. But for asymmetrical molecules, protonating one alcohol might give you a separate product than protonating the other alcohol. So just keep that in mind when you're doing these sorts of problems. For step 2, now that our alcohol is protonated, it becomes H2O plus, or water, right? And that's a very, very good leaving group. So that'll pop off the molecule. And we're left with a carbocation in that case, right? Because we have a carbocation, our molecule wants to become more stable. So there might be some methyl or hydride shifts or things like that, if possible. And then lastly, we will get the remaining alcohol will become deprotonated and form an aldehyde or ketone. So let's take a closer look at what that reaction actually looks like in action. So we're going to look at this pretty simple molecule here. Now this is a symmetrical molecule, which is nice because we only have to worry about one product in that case. And we need to protonate one of the alcohols here. How do we do that? Well, we can use a strong acid, right? If we have a very acidic solution, it's going to kind of force a proton onto one of those alcohols and allow it to become a leaving group. So we treat with sulfuric acid, a very strong acid, and now we have this H2O plus leaving group. Again, very strong leaving group, so that'll pop off, no problem. And we're left with this carbocation here. Now, what we want to do is to get this positive charge on this carbon here because it's attached to the OH and allow us to form a aldehyde or ketone. So how do we do that? Well, we can take one of these methyl groups, right? Take one of the methyl groups and move it over to this carbon, and that will leave us with the positive formal charge on the carbon adjacent the oxygen here, right? And then now it's very easy for us to have this H pop off as an H plus and form a ketone, right? So this is the grand scheme of the Pinacol rearrangement. So just to recap, protonate the alcohol. Alcohol comes off as a leaving group. Carbocation or hydride shifts if possible. Remaining alcohol is deprotonated to form an aldehyde or ketone. Okay, let's do some practice. All right, so for this first practice problem here, this is a nice and symmetrical molecule, so we don't have to worry about multiple products, which is great. So we will start by protonating an alcohol. We'll do the bottom one, for example. And after protonation, again, we have elimination, so the H2O will come off. And now we have to perform a hydride shift or carbocation shift of some sort, right? So we want to get this positive formal charge on this carbon because it's adjacent to the oxygen here. So what we can do is move either one of these bonds. Again, the molecule is symmetrical, so it doesn't matter. But either one of these bonds, we'll choose this one, and move it over to this carbon here. So what we get now is a 6-member ring and a 5-member ring, right? So this 5-member ring is coming from here, right? And then the 6-member ring now is forming between this carbon. So 1, 2, this carbon, 3, 4, 5, and 6, this last carbon, right? Just to help you visualize a little better, this carbon right here is analogous to this one, right? Because now this carbon is forming kind of at the intersection of the 5-member ring that is already existing and the newly forming 6-member ring, right, between these 6 carbons here. Right, so this carbon right here is this carbon, and this carbon now, right, the one that we wanted to move the plus charge to, is this carbon right here. And then now that we have that all set up, we can easily deprotonate that remaining oxygen And what we end up with is this product right here. All right, next one. Okay, so this molecule is not symmetrical. This is asymmetrical, so we have to consider two separate mechanisms for this because we can protonate the two separate alcohols. So let's first focus on protonating the alcohol on the right-hand side. So again, we treat with sulfuric acid. We'll protonate one of the alcohols, so the one on the right. Next, that will come off as a leaving group. And what we can do now is perform a hydride shift, right? Take this hydrogen here and move it over to this carbon to get our plus charge right there, adjacent the oxygen, the remaining oxygen. So we'll do that. And then now we can deprotonate again and form our ketone. Okay. So again, the 4 steps, right? Protonation, elimination, carbocation shift of some sort, and then deprotonation to form our final product. Okay, so let's consider the second product now. This time we're going to protonate the alcohol on the left. So let's go ahead and do that. Again, that'll come off as a leaving group. Now we have a carbocation right here on this carbon. We can move this positive charge here to this carbon adjacent to the oxygen by kind of closing this ring in a little bit and making it a 5-member ring instead of a 6-member ring. All right, so we will again end up with something that looks like this. This carbon, right, corresponds to this carbon here, and this carbon corresponds to this carbon here, right? So now this carbon that was initially in the ring is now forced out of the ring and has the positive charge on it. And then, of course, the last thing we can do is deprotonate the remaining oxygen and end up with our final product right here.